Hello students, my name is Charu. I have done MTech in Information Security from NIT Jalandhar. I have more than 3 years of teaching experience in computer science and qualified GATE examination. The last lecture we talked about this paging technique, and we have practiced the numericals based on paging. I hope paging is clear to you. So the next topic we'll start today is the multi-level paging. So why first question came to your mind that why we require this multi-level paging? Okay, so first let's understand what is this. So multi-level paging is the method in which there are two or more levels of the page table. So from name only, so it is clear that it is a more than one level page table is there, and that page tables are in hierarchical manner. Okay, and the entries of the page of the level 1 page table points to the level 2 page table, and entries of the level 2 page table points to the 3 page table, and so on. This order is followed, and then the entries of the last level page table stores the actual frame information. The actual frame information is in the last level page table. So level 1 contain the single page table, and address of the table is stored in the PTBR, that is the page table base register. Okay, so here it contains PTBR, that contains the level 1 page contains the PTR value that will give you the, this is level 1, this is level 2, this is level 3 page table. Okay, so this contains the address of this one, this will contain the address of this level 3 page table, like so on we have. So why we require the multi-level paging? Why there is requirement? If the page table size is greater than the desired size, then we create one more level. Okay, so this is how we represent the logical address. This is level 1, it will contain P1, page 1, it will contain P2, so on, and last level, after last level we have offset. Okay, and we get the address of the frame from the last level. Okay, so let's see with the help of one example, then it will be clear to you what is multi-level paging and why there is a requirement of the multi-level paging is there. So if the size of the page table is greater than, size if size of the page table is greater than the frame size frame size, then it will not fit in that frame. We know that page table is stored in the frame. So if the size of page table is more, then it will not be able to store in the that particular frame. Okay, in the main memory. Then page table will be divided into, then page table will be divided into pages. Okay. Then the page table will be divided into pages. So let us suppose the physical address space is given to you. Physical address space given to you is 512 MB. Okay. So if I want to calculate the physical address, what it will be? So I have to write this in bits. 2 raised to power 9 into m is 2 raised to power 20. Sorry, 20. Okay. So what it will be? 2 raised to power 29. Okay. So what is the value of PA here? Physical address will be I write the physical address, it will be of 29 bits, right? This is the offset, this is the page number. So how we can calculate the D, that is offset? If the page size is given, let us suppose the page size or the frame size given to you is 4 KB. Page size or the frame size given to you is 4 KB. So if I have to write this in bits, 2 raised to power 2, K is 2 raised to power 10. So total 2 raised to power 12. So what is D here from here? I can calculate D as 12. So I will write D here, D is 12. Then 29 minus 12 will be, how much it will be? 17. It will be 17. So sorry, if this is the physical address, then here we have to store the frame number. So it will be F, not P. So F value will be 17. So how many number of frames will be there? Number of frames will be 2 raised to power 17, right? So let me calculate the number of pages. Number of pages will be calculated by, let us suppose the logical address space is given to you as 16 GB. 16 GB. So here, if I take the logical address, then it is combination of P and D. So if I have to write this logical address space in bits, then how I will write? 2 raised to power 4. G is 2 raised to power 30. So it will be 2 raised to power 34. So it will be of 34 bits, the logical address. And D is same. What is the value of D here? 12. So I will write 12 here. 34 minus 12, what is it? It is 22, right? So we get the P as 22. So the number of pages will be 22. The same numerical type of numerical we have solved earlier also. So you might have idea how to get the number of pages and number of frames here. So see, now I have the number of frames. If I talk about the main memory will contain the number of frames. What is the value? 2 raised to power 17, because here number of frames are 2 raised to power 17. Okay, if I talk about the main memory scenario. And how many the number of pages are there? Pages will be 2 raised to power 22 pages will be there. And what is the size of each page? That is 4. It is given as 4 KB. It is given as 4 KB. So if I have to calculate the number of page entries, can I calculate it? Page entries, how it will be given? It will be given, how many number of pages are there? 2 raised to power 22. Number of page entries will be number of pages only, na? That's why 2 raised to power 22. So from here I can able to find out the page size. That is page table size. Page table size I can be able to find out, that is number of pages, that is number of page entries 2 raised to power 22 multiply by page table entry size. Here page table entry size is also given. Page table entry size is also given. Let us suppose it is 2 bytes. So it is multiplied by page table entry size into number of entries. There you get the size of page table. So how much it will be? 2 raised to power 1 into 2 raised to power 22. It will be somewhere 2 raised to power 3 into 2 raised to power 20 if I have to write. What is 2 raised to power 20? It is M. So it will be 8 MB. It will be page table size will be equals to 8 MB. और पेज size कितना दिया है तुम्हें? 4 KB. But we know it should be less than the frame size or page size. Otherwise it will not be able to accommodate it. So from here we can get the idea that we require the multi-level paging because it can't accommodate in that particular frame, because 8 MB is greater in size than 4 KB. So we have to do the multi-level paging. So now what happens? Now scroll down. So now what I will do is, I will now the page table will be divided into pages, because the page table size is greater than the frame size. Now I will divide 8 MB by 4 KB. What it will be? It will be 2 raised to power 3 into 2 raised to power 20 divided by 2 raised to power 2 into 2 raised to power 10, because K is 10. So it will comes out to be 2 raised to power 11. 2 raised to power 11. So this entries, so if I talk about outer page table, then this is the outer page table level 1. So it will be, outer page table will be, how many entries will be there? 2 raised to power 11 entries will be there. Okay, so if you have to calculate the size of the outer page, so how it will be? Because it is divided, size of page table 1, that is this one, outer page table. So what it will be? 2 raised to power 11 into 2 raised to power 1. So what it will be? 2 raised to power 12. If I calculate it, 2 raised to power 2 into 2 raised to power 10 is 4 KB. So 4 KB can be accommodated in the 4 KB, that is a frame size. Now we will not do the further paging, means we will stop here. It will fit in the frame size and no other further outer page table is required. Okay, so what scenario it will be like? So P1, P2 and this offset. So this P1 will be pointing to the outer page table. This is the outer page table, From here, what is the value of D? 12. And what is the value of P1? We have calculated 11. So whole, if LA's whole is, I think, 34. So it is whole 34. 34 minus 12 minus 11 is 11 only. So this P2 second page number is also 11. So it will point here. Then here you will get the value of P1. From here you will get the value of P2. Somewhere here. So it is the inner page table. Okay. Inner page table. So it will point here. Then last, that is the main memory. Here the number of frames will be there. Here you will get the frame number with the help of. I hope this multi-level paging is clear to you. So after this, the mapping is also done. So I hope this is clear to you. We'll practice one more numerical gate question based on the paging. Okay. So there is GATE 2013 question is there based on multi-level paging. So it says a computer uses 46-bit virtual address, 46-bit virtual address and 32-bit physical address. and a 3-level page table organization is followed. So the page table base register stores the base address of the first level table, that is T1, which occupies exactly one page. Then each entry of T1 stores the base address of the page of the second table. Each entry T2 stores the base address of the page of the third level, that is T3. Each T3 stores a page table entry. Okay, page table entry. That page table entry is 32 bits in size. The processor used in the computer has 1 MB 16-way set associative virtually indexed physically tagged cache, and the cache block size is 64 bytes. You have to calculate the size of page in KB in this computer, and this is numerical answer type. It may be now, but there are options given, so I have not mentioned options here. You can pause the video and you can try yourself. If you are not able to solve it, then you can unpause the video and you can continue watching the video. I will provide you the solution here. Okay, but let's try to practice this first, then you see the solution. Okay, so what are the solution I am providing here for this numerical? So here this is level 1 paging, so T1, this is T2, this is page table 3, page table 2, page table 1. It is storing the PTBR, storing the base value in the register that is pointing to T2, then T3. Okay, so 3-level paging is followed here. So let's write what is the logical address given. Logical address is virtual address, same thing, 46 bits. What is the physical address? Physical address is 32 bits. Okay, so first level page has only one page. So let me calculate the page table entry size. What is given here? Page table entry size is given as 32 bits. 32 bits. This is given. So let me write it in. So if I have to write in bytes, it will be 4 bytes. Right. So what is the page size? They have asked that what is the page size. Let me calculate here. So let page size has n bits. Let the page size has n bits. So page size equals to 2 raised to power n. Page size will be 2 raised to power n bytes. Okay. So that is equals to number of entries in the page into size of each location. Size of each location is 1 byte. So number of entries here 2 raised to power n and size is 1 byte. So it will become 2 raised to power n bytes. Okay. So since the first level page has one page, so number of entries in the table 1 will be, so number of entries in table 1 equals to size of the page table, size of the page table divided by size of each page table entry, size of each page table entry. Okay, so what it will be if I am talking about T1? So it will be 2 raised to power n bytes divided by 4 byte. Okay, so from here byte will get cancelled with byte. It will be 2 raised to power n minus 2. This is the number of entries in the table 1. Okay, so We minimize so here number of entries in the page table 1 will be 2 raised to power n minus 2. So size of, let me calculate for level 2, size of page table 2, okay, or T2. So it will be number of entries in T1 multiply by size of each page. What it will be? It will be 2 raised to power n minus 2. This one we have find it out into 2 raised to power n. So it will be size of page table 2 will be 2 raised to power 2 n minus 2. So it will be 2 raised to power n minus 2 bytes. So here the size of T2 is known to us now. So now we can able to find the number of entries in T2. And we find out same size of the page table 2 and divided by page table entry size. What it will be? 2 raised to power 2n minus 2. We have find it out here. B divided by what is the page table entry size? That is 4 bytes. It will get cancelled with, it will be 2 raised to power 2n minus. So this much number of pages are there, or this much number of entries in the T3 level, right? So let me calculate the size of page table 3 now. Page table 3 or T3, what it will be? 2 raised to power 2n minus 4 number of entries in the T2 into the size of page. What is the size of page? Size of the pages we have calculated here 2 raised to power n bytes. So what it will be? It will be 2 raised to power 3n minus 4 bytes. Got it? Now what we have to find? Now we have to see what is the logical address, that is 46 bits. It's given. Okay. So the logical address space, what it will be? 2 raised to power 46 bytes. If I have to write the logical address space, that will go into the power. It will become 2 raised to power 46 bytes. Right? So number of pages will be logical address space divided by page size. What it will be? It will be number of pages will be 2 raised to power 46 bytes divided by page size is 2 raised to power n bytes. Will get cancelled. It will be 2 raised to power 46 minus n. So from here also we get the this number of pages. From here also we got the number of that is the size of the page table, and from there we get the entries we have not calculated here, right? Size of page table we have calculated. Number of entries will be 2 raised to power 3n minus 4 divided by 2 raised to power 2 bytes. So it will get cancelled. It will be 2 raised to power 3n minus 6 number of entries in the T3. Here also we got the number of entries, that is number of pages. We can if I mark it 1 2, so from 1 and 2 what we will get? We will get 2 raised to power 3n minus 6 equals to 2 raised to power 46 minus n. So base are same. I can write it like this. So it will be 4n equals to 52. What is the value of n here? N will be 13 here. 52 divided by 4 is n is 13. if n is 13, here, what is the page size? We have to calculate the page size in KB. Page size will be equals to, okay, 2 raised to power 13 bytes. So it will be 2 raised to power n bytes, because size of each location is 1 byte. So 2 raised to power 3 into 2 raised to power 10, because we have to calculate it in KB. So it will be 8 KB. The page size will be, the answer will be 8 KB. So the correct answer is 8 KB. I hope this numerical is clear to you. So this was asked in the GATE 2013. Next one is TLB, that is translation leukocyte buffer. So in paging, the CPU assess 2 times referring to the main memory. Main memory को 2 बार refer करता है. First for the page map table and second time to find the page in the main memory by finding the particular frame, right? So the time of execution is increasing. So what we have done is we have placed a TLB, that is the hardware, not software. Okay, TLB is the hardware. Remember that. Not a software, it is a hardware. So it is a special cache used for the keeping the track of recently used transactions. TLB contain the page table entries that have mostly been used. Okay, so I told you that that is paging is taking more time, so that's why the one special cache, that is the hardware, we have placed here, that contains the most recently used transaction. So with the help of virtual address, processor examines the TLB. If the page entry is present, that is called as TLB hit. If the frame number is retrieved and real address is formed, if the page table entry is not found in the TLB, then it is called as TLB miss. If the page number is used as index while processing page table, then TLB first checks if page is already present in the memory. If it is not present in the main memory also, then the page fault occurs. Okay, then TLB is updated to include the new page entry. अगर इसमें नहीं मिलता है तो TLB miss हो जाएगा. Then whenever TLB miss, अगर उसके बाद भी मुझे फ्रेम, वो पर्टिकुलर फ्रेम वहाँ फिजिकल एड्रेस में नहीं मिलता है, then that page is not found in the particular frames present in the physical address, then the page fault occurs. Then TLB will update that particular page with the new page entry. This is the concept. Just to speed up the execution, that TLB concept came here. Okay. So see here what is there. So there can be two scenarios, either the TLB miss or TLB hit. Suppose TLB hit occurs. What is the scenario in TLB hit? First, CPU will generate the logical address here. Here CPU will generate the logical address. Logical address is the combination of page number and offset. From there, we will check whether that page is present in the cache or not. So, second is it is checked in the TLB. It is checked in TLB. So, hit कब होगा? When the corresponding frame is retrieved. When corresponding frame number is retrieved, okay, which will tell that where in the main memory that page lies. Okay, then the TLB hit will occur. Okay, then it will find out the particular frame and it will go to that frame and fetch that page from the physical memory. Okay, so second condition will be when TLB miss will be there. TLB miss. The first step is that only the CPU will generate the logical address. Okay, then second step will also be same. It is checked in the TLB, but now it is not present in the TLB. Then TLB miss occurs. Then page number, what happens? Page number is matched in the page number is no, we don't find in cache, so it will come here. It will find in the page table. It is page number is matched in the page table which is residing in the main memory. Okay. Next step is corresponding frame number will be retrieved now, and which tell you the frame number which is present in the main memory, right? Next step, then TLB will be updated in the end by checking the corresponding frame number. Then TLB will be updated with the new page table entry. With the new page table entry. If still the page is not found, then replacement algorithms will be adopted. That is FIFO, LRU, MRU. All will study later on, but all that replacement algorithms will be followed if there is no space in the main memory, right? So since the execution time is less here due to presence of TLB, so we will calculate the effective memory access time. Effective memory access time, that will be given as, so H multiplied by T plus M plus 1 minus H T plus 2M. Okay, so see here, H is the hit ratio here. H is the hit ratio. T is the TLB assess time. Okay. The time it is taking to assess the TLB, it is T, and M is the memory assess time. Memory assess time. See here, we have written this thing. H is the hit ratio. We found the page. Okay. So how much time it will take? First it will look into the TLB and then it will assess the main memory. T plus M simply. So there may be scenario when there is miss occurs, means you don't get the page in the TLB. Then 1 minus H will be there, miss ratio. Okay. And what we will do, first we have to look in the TLB कि पेज नहीं मिला, यहाँ पे देखना पड़ेगा T plus twice we are first we are assessing the page table in the main memory, then we are seeing the corresponding frame number in the physical memory, or you can say that main memory. There we found assess the page in a particular frame. So two times we are assessing the main memory, so that's why 2M here. So it short form we can write it as EMAT, effective memory access time. It is given by H T plus M plus 1 minus H T plus 2M. I hope this is clear to you. So let's practice some questions based on TLB. It is also very important topic from GATE point of view. So let's solve the GATE 2014 question. This is simple. So consider a paging hardware with a TLB. TLB is used. Assume that the entire page table and all the pages are there in the physical memory. It takes 10 milliseconds to search the TLB and 80 milliseconds to access the physical memory. If TLB hit ratio is point 6, the effective memory access time, EMAT, in milliseconds we have to calculate, and the 4 options are given. So let us write the formula for effective memory access time. What is it? Hit ratio. I have to assess the TLB plus I have to assess the memory. Okay. If there is miss occurs, then I have to assess the TLB first to find out the page. If it doesn't found in that TLB, then I have to assess the memory twice. Okay. So what is the H here? 0.6. It is given, hit ratio is given. Then TLB miss 1 minus H will be 0.4, 1 minus 0.6. Then time taken to assess TLB, that is T. T is given 10 milliseconds. Then time taken to assess main memory. Main memory को assess करने के लिए time given है 80 milliseconds. Let me put all these values here. Okay. These values are given. I am putting in this formula. H is 0.6, T is 10, plus M is 80, plus 1 minus H is 0.4, then T is 10 plus 2 multiplied by 80. Okay. So 0.6 multiplied by 90 plus 0.4 multiplied by, it is 161 and 70. Okay. So it will be somewhat 122. When you calculate it, it will comes out to be 122. The second option is correct option. So I hope this is clear to you. Second numerical is to consider a paging hardware with TLB. Okay, assume that this is the same question, I think. Same question. So the question given here. So consider, this is GATE 2020 question. Consider paging system that uses one level page table residing in the main memory and a TLB for address translation. Okay. Each main memory access takes 100 nanoseconds and TLB lookup takes 20 nanoseconds. Each page transfer to and from the disk takes 5000 nanoseconds. Assume that the TLB hit ratio is 95%, page fault rate is 10%. Assume that the 20% total page fault occur and a dirty page has to be written back to the disk before the required page is read from the disk. Okay. TLB update time is negligible. Update time is considered to be 0. The average memory access time in nanoseconds we have to calculate. So for this you have to know some concept of what is this dirty page. So dirty page, what is this dirty page? So sometimes page is replaced or page is modified, that is called as dirty page. So its backup of all the data which is modified is done when it is placed in the main memory to the disk. Okay. So that is the dirty page. And here no page display. So see here we have to calculate the access time. Let me write the formula. Access time as this time of TLB miss and plus disk access time plus memory access time. Okay, so this is the scenario when there is no page replacement is required. When there is no page replacement is required, means there is some space in the main memory. Okay, so if there is requirement of page replacement, means there is no empty space in the main memory, then what is the scenario? Then the access time will be equals to TLB miss. Okay, under TLB miss, this scenario will be there. That is whether the page replacement will be there or page replacement is not there. Okay, only in the case of TLB miss. But in TLB hit, there is no such scenario for the page replacement, because already we got the page in the TLB. So it will be TLB miss plus 2 times we have to assess the disk. So disk access time will be multiplied by 2, because twice the disk will be accessed, plus memory access time. Okay, memory access time. So the formula will be, if I write the effective memory access time, it will be equals to h multiplied by t plus m plus 1 minus h multiply by, this is when the TLB hit occurs, 1 minus h, 1 minus p multiply by 2 multiply by m plus p multiply by 1 minus dp. This dp is the page fault with the dirty page hit rate. Okay, then d plus m plus dp twice of d plus m plus t. So here this is the scenario when TLB miss will occur. Then there can be when page replacement will be there, and page there is no requirement of the page replacement. Okay, whether you get the page fault or whether you are not getting the page fault, that is the scenario. So let me write here, m is the main memory access time, d is the disk access time. Here d is the disk access time. D is the disk access time, and dp here is the page fault with dirty page hit rate. Okay. And d is the m is the main memory access time, and t is the TLB access time, and you know that h is the TLB hit ratio. Okay, so all the values are given in the question, so you have to put the values. So h is, let me take h here, h is the hit ratio, that is given 95%. I can write it as 0.95. Okay, and your page fault uh, access time, that is given 10, rate is given 10%, so I can write it 0.1. Then t is given 20 nanoseconds, and then main memory access time 100 nanoseconds. Everything is given in nanoseconds only. 5000 nanoseconds discusses time, and DP is given as 20%, right? Yeah, so I can write it 0.2. So all the values are given. Let me put here. So what it will be? So when you calculate the effective memory access time by putting all the values here, what it will be? H is 0.95, T is 20, plus M is 100, plus 1 minus H. 1 minus H is 1 minus 0.95. Then what is there? 1 minus P. P is 0.1 into 2 into M. M is 100 nanoseconds. Then I am writing here. Yeah, plus P. P is 0.1. Then 1 minus dp is 0.2, then discusses time is 5000 nanoseconds, plus m is 100, plus dp is 0.2, 2 multiplied by discusses time 5000 plus 100 plus t is 20. When you calculate it, it will comes out to be 154.5 nanoseconds. Okay, so when you solve this whole thing, it will comes out to be 154.5 nanoseconds. I hope the concept is clear to you. If you have any doubts, you can comment below, or you can mail also. The mail address is given to you. Okay, so this was all about the multi-level paging and TLB. Okay, thank you.